Hello. This podcast is on vertical uniform acceleration. Specifically, we're going to look at free fall, then we're going to take a quantitative analysis of free fall. We're going to look at free rise, also going to quantitatively analyze free rise, and then we're going to look at what's known as vertical projectile motion. Let's take a look at a vertical motion we call free fall. I'm going to be dropping a golf ball from about 2 meters. Let's watch it in slow motion. So free fall is the falling motion of an object when gravity is the only force acting on it. It's a type of uniform acceleration. Free fall can involve something being dropped, like I dropped the golf ball, which means it has an initial velocity of 0, it's at rest, or it can be thrown downward, which means it has a velocity greater than 0 in the negative direction. We consider it free fall if the air resistance is very small, in fact small enough that we can ignore its impact. So let's take a look at what it looks like quantitatively. And here we have in figure 1 a position versus time free fall. We notice a curve that we have seen before with uniform accelerated motion. And this curve goes from flatter to steeper because the object is speeding up. In fact, if we go back to our previous slide, we can see as the ball is dropped, I've marked the position every 5/100ths of a second. And we can see that as time goes on, the change in position, the displacement, gets larger and larger. So that's a sign of something speeding up. If we look at the time versus position chart, we can see the position every 5/100ths of a second. And notice that the displacement, delta x, increases as time goes on. It was just over 1 centimeter here, or 12 millimeters. Then it increased to 36 millimeters, 61 millimeters, 85 millimeters, and so on. Because it's uniform acceleration, the rate at which displacement increases is constant. Notice that the increase from 12 millimeters to 36 millimeters was an increase of 24.5 millimeters. So every 5/100ths of a second, the displacement is increasing by 24.5 millimeters in the negative direction. Let's take a look at the velocity time graph for free fall. So here we see the object was dropped starting at rest, 0 meters per second, and we can see that it speeds up in the negative direction. 0.6 of a second later, it's at almost -6 meters per second. The graph, as we've seen before with other types of accelerated motion, is a straight line with a constant slope. If we look at the time versus velocity graph, we can see that every 5/100ths of a second, the velocity is increasing by 49/100ths of a meter per second, increasing in the negative direction. We can see the change in velocity is constant. It's -0.49 meters per second every 5/100ths of a second. And that's a key of uniform acceleration. A key characteristic of uniform acceleration is that the change in velocity is going to be constant. So far, we've been looking at the data for the golf ball, and that involves very small values of time, displacement, and velocity. Let's talk about free fall in general. The acceleration will tell us the changes in velocity and position. Let's look at that a little closer. Velocity. Every second, the velocity increases by the amount of the acceleration. Displacement, also known as change in position. During the first second, the displacement is half the amount of the acceleration, and every second after that, the displacement changes by the amount of the acceleration. Let's take a look at an object in free fall on Earth. And the acceleration for free fall is -9.8 meters per second squared. That's the acceleration caused by gravity. Here's our time, velocity, displacement, and position chart. The acceleration is -9.8 meters per second squared, and that means every second the velocity is increasing by -9.8 meters per second. It started at 0, went to negative 9.8, and so on. Let's look at the displacement. We notice that for the first second, the displacement was negative 4.9 meters. That's half of the acceleration. And then every second after that, the displacement is increasing by 9.8 meters in the negative direction. Let's take a look at free fall on the moon. Here we have an acceleration of negative 1.6 meters per second. We're going to drop something from rest, 0 velocity, at a position of 0. Notice that the displacement for the first second is half the acceleration, so it's going to be negative 0.8 meters. The velocity changes by the amount of the acceleration every second. So after 1 second, the velocity is now 1.6 meters per second in the negative direction. The displacement from 1 second to 2 seconds increases by 1.6 meters from the initial displacement. Well, that brings our position to negative 3.2 meters at the end of 2 seconds. Pause the video and take a few minutes to complete this table for free fall on the moon. Here are the answers. Pause the video and see how you did. Let's take a look at free fall on a mystery planet where we don't know the acceleration, and we're going to see if we can figure out what the acceleration is. Here is time, velocity, displacement, and position. We can see that the velocity is increasing by 25 meters per second in the negative direction every second. We see that displacement during the first second was negative 12.5 meters, and we can see that the displacement is increasing by 25 meters every second that goes by. Pause the video and take a minute to find out the acceleration on this mystery planet. If you said the acceleration was negative 25 meters per second squared, you're right, and that happens to be the acceleration caused by gravity on the planet Jupiter. Let's move on and talk about another vertical motion known as free rise. Here the golf ball is bouncing up from the floor. And again, this is in slow motion. Free rise is the rising motion of an object when gravity is the only force acting on it. So once this golf ball left the floor, as it went up in the air, the only force acting on it was gravity. It too is uniform, aka constant acceleration. For free rise to occur, the object has to be launched with an initial velocity greater than 0 in the positive direction. As with free fall, when we have free rise, we're assuming the air resistance is very small, small enough that we can ignore it. Notice, as time goes on, these dots represent every 5/100ths of a second, and we can see initially the displacement or change in position during the first 5/100ths of a second is pretty large, but as time goes on, the displacement gets smaller and smaller, and eventually the ball briefly comes to a stop at its peak height. Let's look at the position time graph for free rise. We've seen this before, a curve that goes from steeper slope to flatter slope, and that's a sign of an object that's slowing down. Looking at the table, we can see the position continues to increase, but the amount that the displacement changes is getting smaller and smaller. In fact, 24.5 millimeters smaller every 5/100ths of a second. Looking at our velocity timeline, we can see that it starts away from the time axis and heads towards 0, an indication that it's slowing down, and it's a straight line with a constant slope. If we take a look at our time velocity and change in velocity chart, we can see that every 5/100ths of a second, the velocity is changing by 4.9 meters per second in the negative direction. And so the change in velocity is constant as the object slows down. Let's look at free rise in the general sense. The acceleration tells us the changes in velocity and position, just like it did for free fall. Velocity. Every second the velocity changes by the amount of the acceleration. For displacement, during the first second, the displacement is the initial velocity minus half of the amount of the acceleration. And then every second after that, the displacement changes by the amount of the acceleration. So let's take a look at free rise on Earth. The acceleration due to gravity is 9.8 meters per second squared in the negative direction. And for this specific example, we're going to start with an initial velocity of 49 meters per second in the positive direction. So here's our table showing time, velocity, displacement, and position. As time goes on, you can see every second the velocity is changing. In this case, it's decreasing by 9.8 meters per second. And then if we look at the displacement, the initial displacement is 49 minus half of the acceleration, which is 4.9, and that gives us a displacement of 44.1 meters. And then we can see every second that goes by, the displacement is going to decrease by 9.8 meters every second. And we can see that in this case, the object reached a peak height of 122.5 meters. Now, let's have you try your hand at filling out the time, velocity, displacement, and position table for free rise on the moon. So at time 0, we have an initial velocity of 8 meters per second in the positive direction and a starting position of 0 meters. The acceleration on the moon is 1.6 meters per second squared in the negative direction. Pause the video and take a few minutes to complete this table. All finished? Let's see how you did. So the acceleration is -6 meters per second squared, so the velocity is going to decrease by 1.6 meters per second every second. And the displacement is going to start out by being the velocity minus half of the acceleration. So that's going to be a displacement of 7.2 meters. And then the displacement is going to decrease by 1.6 meters every second after that. And of course, you can find the position by simply taking the displacement and adding it to the previous position. Okay, let's move on and tackle another challenge. Let's calculate the free rise on Jupiter, where the acceleration is -25 meters per second squared. Here, the object has an initial velocity in the positive direction of 125 meters per second, and the starting position is 0. Pause the video and take a few minutes to complete this table. Are you finished? Well, let's take a look. Because the acceleration was 25 meters per second, in the negative direction, the velocity is going to decrease by 25 meters a second every second until it reaches 0. Our displacement is going to be the initial velocity minus half the acceleration, so that will give us 112.5 meters as the displacement during the first second. And then after that, the displacement is going to decrease by 25 meters every subsequent second. And we can see this object reaches its peak height of 312.5 meters in 5 seconds. Let's move on to vertical projectile motion. Here we see the golf ball bouncing up in slow motion, reaching its peak, and speeding back down towards the floor. This is what's known as vertical projectile motion. It's the combination of free rise and free fall. In this case, the object has to be launched with an initial velocity greater than 0 in the positive direction. And once the object is launched, gravity is the only force acting on it. It's uniform acceleration. And once again, air resistance is very small, so small that we can ignore it. Well, let's take a look at the position time graph. Not surprisingly, it is this arch shape that we've seen before when we've pushed something up a hill and let it roll back down. We can see a line of symmetry here at half a second. This first part, the object is slowing down. It is in free rise. It reaches its peak and momentarily stops moving, and then it speeds up as it heads down towards the floor. This line here at half a second is a symmetry of position. Notice these positions are all the same when you're equal distance from this line of symmetry. Now let's take a look at the velocity time graph, and we can see here that we start with an initial velocity of just under 5 meters per second. We slow down, we reach 0 meters per second, change directions, and then speed up in the negative direction as the object is heading down. And we reach a final velocity when it hits the floor of 4.9 meters per second in the negative direction. There is a line of symmetry here also. It's perpendicular to our velocity line, and it too happens at half a second. But notice these velocities, as you move away from the line of symmetry, these velocities are the same speed, just in the opposite direction. So their number values are the same, it's just that they're headed in the opposite direction. The initial velocity that an object is launched with will be the velocity that it returns back to the floor, only in the negative direction. Well, this ends our podcast on vertical accelerated motion. Specifically, we studied free fall, free rise, and the combination of the two known as vertical projectile motion. Hope you found this podcast helpful, and have a good day.